Hi everyone, this is Professor Chia, and today I wanted us to talk about statistical process control and to answer the question of what is SPC and where does it add value to our business, especially within the manufacturing environment. So for this video, I'm going to basically be looking at the first four objectives that are listed in Chapter 6, Supplement 6, which basically introduces us to the SPC control chart. And we want to look at what is an SPC chart and what are the major different types of charts that we have when we talk of statistical process control. And then I'll go into an illustration of how do we go about doing or building an SPC chart in Excel, okay? And in the second video, I'll go over how to go about building a P chart and a C chart, which provide us with slightly different information. And finally, I'll wrap it up by discussing process capability and the different metrics that are used to determine or to calculate process capability, okay? So statistical process control is basically a scientific technique that we use to try and gain a measure of control over any production process. And I would give an example here where if we had a factory that manufactured bars of tofu, and each bar was supposed to be 1 pound exactly, okay? So if we are continuously manufacturing bars of tofu and each pound has to be 1 pound, what you would find if you ate each and every single bar of tofu produced is that they won't exactly weigh 1 pound. Okay, one might weigh slightly over a pound, say a pound, 1.1 pounds, another might weigh 0.98 pounds, another might weigh 0.95 pounds. So they won't always be exactly 1 pound. But the objective is that we should try and aim for as much as possible to be at 1 pound for each and every bar of tofu, okay? Now, what's the problem with us not being able to meet this target of 1 pound? Well, for one, if we are marketing the product as being 1 pound and our customers go out and weigh this tofu and they find that the pound is consistently underweight, the tofu is consistently underweight, then it means that we're shortchanging the customers, and that could lead to a whole bunch of legal problems. As you remember, Subway had an issue with this where their foot-long subs were actually slightly less than a foot long, okay? So an alternative might be, why don't we consistently make them slightly bigger than 1 pound so that we never fall short? The problem with that is that you're losing money, okay? So for every extra fraction of a pound that you add to that 1 pound of tofu, you're giving product out for free. And so the company is losing money. So a better alternative is to find a way to consistently be pretty close to that 1 pound. And if we could find a way to measure this and to ensure that we're consistently close to 1 pound within some acceptable range, then we should be fine. And that's exactly what SPC is all about. How do we ensure that we're within some acceptable range, okay? So if our target is 1 pound, it could be that we'd be okay with accepting any bar of tofu that's within the range of 0.95 to 1.05. But again, we would need to be able to figure out what should that upper limit and that lower limit be. And so that's what SPC is all about. So let's go and look at some examples that might help illustrate this slightly better. So when we talk about assignable causes, when we're looking at SPC and trying to figure out what is it that's causing a problem in our manufacturing processes, there are both natural causes and then there are what we call assignable causes. Natural causes could be anything from an earthquake or a hurricane, things that we really have no control over. And as such, it might not make sense for us to try and factor that into our equation. But assignable causes could be things that we have control over. Okay, so for example, if we have an employee who's consistently tardy or consistently puts too much product into the mix, that's something that could actually be caught and could actually be controlled for, okay? So we are interested here in variability that arises not from natural causes, but arises from assignable causes, okay? So we'll try and figure out what are the bad causes. Let's fix those. If there's anything that makes our processes better, let's incorporate those and make our processes even better, okay? So SPC is statistical in nature, and when we talk of SPC, we usually go off what's called the normal curve, okay? And the normal curve comes from this perception that if we are to measure, say for example, if we go back to our tofu case, for example, if we are to measure bars of tofu in the long term, what we'd end up finding is that yes, there'll be some variability, but if we are to get the average over time, you'd find that if the average was 1 pound, a whole bunch of different bars of tofu should be falling around 1 pound. There'll be some falling below, some above, but most of the time, if we took 1 million bars of tofu, you'd start to notice a trend where most of the bars of tofu should fall close to 1 pound's worth of weight, okay? And if you had to draw this, you end up having something where there might be some that are slightly underweight and some other bars that might be overweight. But overall, in the long term, what you end up finding is that if your process is in control or near control, you end up having what's called a normal distribution, which is usually bell-shaped and with a concentration right about the mean of the data, okay? So we want to ensure that our processes fall within some range, and to ensure that we don't have product falling into this low and upper regions here, because in those instances, we're either losing money or we are possibly losing customers if they feel that we're shortchanging them, okay? So the normal distribution becomes a pretty significant part of what we're doing here, and everything that we will be doing going forward for this chapter, we're going to assume has possibly a normal distribution to the data, okay? So let's go into an example of what we should expect to see, okay? So when we're building a control chart, this is what we typically want to have on our control chart. We're going to have what's called your, let me bring my pencil out again, your upper control limit and your lower control limit. And you're going to have the mean or average to your data, okay? Now, for a process to be considered as being in control, it has to meet certain requirements. One, all the data points that you're going to have in your sample should fall within this range from the upper to the lower control limits. And at the same time, there shouldn't be a trend to your data. So for example, all the data points might be within the upper and lower control limits, but if I had data points that looked something like this, I would say my process is not in control. Why? The data seems to show that our weights are getting bigger, and if left unchecked, chances are that sometime down the road, we're going to have a situation where our process falls out of control, okay? So we want to have randomness to each and every data point, such that we have some data points above, some data points below, and we don't have a run of data going in, showing some measure of trend in a certain direction, okay? If anything, we want to make sure if it was to be a trend line, it should be something that's flat, which is not really a trend line, it just shows that everything is close to the mean, okay? So let's go ahead and I'll clear this and look at certain examples of how to go about building a control chart. And we're going to start here by examining the X bar chart and an R chart. Okay, so X bar charts are the most basic and the most commonly used bar charts, and these show how close the different sample data aligns with that measure of central tendency. In this case, we're going to use the mean as our measure of central tendency. So the X chart just basically tracks how close are the different data points to that central point, that mean value that we're trying to aim at. Okay. The R chart is also called a range chart, and it basically shows you the range of data, because we could have data points above and below the mean. We just want to know how wide is that dispersion. Are they close to the mean? Are they widely dispersed? So the R chart enables us to capture that information. Okay, so combining these two charts together enabled us to figure out whether or not our processes are actually in control. Okay, so what do we need to be able to create these two charts? We're going to need a minimum the mean of the sampling distribution. Okay, and then we're going to need the standard deviation of the sampling distribution. Okay, so the mean is just basically we take all the different values in our sample and we average them out and come up with a number. And we're going to assume that that mean is going to closely approach the population mean, meaning that if we had a sample of, say, 50 units, whatever average we get for that 50 units should closely approximate what the average would be for 1,000,000 units, okay, which would be our population mean. Again, for the standard deviation, we're going to assume that the dispersion within that sample is going to closely mimic what the standard deviation or dispersion would be in the general population. But because we realize that a sample of, say, 10, 15, 20, 30 might not exactly mimic what the population would be, we adjust for that by dividing the sample standard deviation, the population standard deviation, by the sample size, and come up with a factor for the sample standard deviation, which is usually slightly smaller than the standard deviation for the population. Okay, so the other thing that we're going to need here is what we call our z-scores, and the z-scores are tied into the standard deviations. Okay, I'll discuss that when we go into the Excel spreadsheet. Okay, so let's go into a spreadsheet, and actually, instead of looking at the theory in your PowerPoint, which by now you should have already covered, let me pull this up here. Okay, so let's start off by assuming that we've taken a sample, 12 samples actually, from a regular manufacturing operation, and we have here weights associated with each sample. So we had 12 samples, and each sample we took 9 pieces of product and got their weights. Okay, so this could be as simple as saying that this is 8 o'clock in the morning. We're going to take one sample, and then from when we say one sample, we're going to take 9 different pieces of product within that one time period, and that becomes our sample 1. At, say, 8:30, we go ahead and take another sample, 8:30, and the second sample also comes up with a whole bunch of different measurements, and so on and so forth. Okay, now using this information, we can go ahead and calculate our X bar charts. Okay, the first thing that we need to figure out is what's the average for every sample that was taken. Okay, and in Excel, that's a simple average calculation where you use the average function. Take your averages for each and every sample, and after getting those averages, you're going to calculate your average of all the averages. Okay, so to do that, I'll get my mean of means by using the average. Oh, that's not how to write average. Average of these 12 averages that we have here. Okay, so now with this figure of 16, which is our mean of means, we can now go ahead and calculate our X bar charts. So let's go ahead and do that in the second tab here. Okay, so we've summarized, these are the averages that we had for all the 12 different samples. Now, once we do that, we need to figure out, we're not building our control charts, we need to figure out what's our upper control limit and what's the lower control limit. Okay, so to do that, we need first to calculate the mean of means, which is what we did here, 16. So I'm going to put that here as a reference. And if we are to draw that, that's that center line on your control chart. Okay, and then we're going to need a z value, and the z value basically tells you how many of the data points you want to incorporate. If we use a z value of 3, it means we're pretty much incorporating every data point that should be available in the data. Okay, and z value of 3 will be what's most commonly used, and that's what I want us to use here. And then we're going to need to know how large is the sample size for each sample that's taken. So we had 12 samples. Each sample had 9 units of product in the sample. And then the final thing that we need to know, in this case here, one thing I forgot to mention is when you're running your SPC, you have to ask yourself, do we know the standard deviation of the data or do we not know? Okay. So in this first example here, we're going to assume that using historical data, we know what the population standard deviation is. And I believe the textbook gave it as 1, okay, meaning that on average, the dispersion around this mean is approximately 1 unit or 1 unit, okay? So 1 pound, sorry. And that's the standard deviation of the population. Now we need the standard deviation of sample mean, and for that we divide this standard deviation by the square root of your count. Okay, so that will equal 1 divided by the square root of 9. And we put some additional parentheses here. Okay. So with that, now we can go ahead and calculate the our X bar chart. So let me go here and put the formula for our X bar chart as X bar plus Z multiplied by your sample standard deviation. Okay, so that's plus or minus, because we're going to have an upper limit and a lower limit. The lower limit, we subtract this from your mean that of 16, and for your upper limit, you add this, your z-score multiplied by the sample standard deviation. Okay, so clear this drawing, and I'm going to go ahead and calculate our upper control limit as being your 16 plus your z-score, z value of 3, multiplied by what we have here. Okay, and that gives us an upper control limit of 17. Could have some decimal points here, but no, we don't have any. Okay, and the next thing I'll calculate is my lower control limit, so LCL. And for that, we again do the same thing. You get your mean of sample means minus your Z multiplied by your sample standard deviation. Okay, and then our sample mean here was given as 16. Okay, so that's the information we have here. Okay, so with just these 3 data points, we now have the beginnings of that template that we're going to need to make our statistical process control chart. So we have our lower control limit, our mean, and our upper control limit. Okay, and we're told that this is 15, 16, and 17. Okay, 1, 2, 3. So we had a total of 12 samples. So I'm going to add this to 12. So for the first stage of this whole process, if I was to graph this out, let's go ahead and do that right now. Insert chart. and I'm going to use a line chart. All that this would give us would be your lower control limit, your mean, and your upper control limit. Okay. Now, the next thing that I'm going to do is plug in this information that we have for the averages that we have here. Okay. And this will tell me whether or not our data points fall within the range that we have here. So I'm going to add this here. And let's make this slightly more fancy, add some borders. Bit smaller. So I'm going to rerun this chart and include that new additional information. Insert chart. I'm going to add this chart right here. Okay, and it looks tiny, so I'm going to adjust my settings on the side here. Format, axis, and we're going to start off here. Our lowest value here is like what? Around 14.2. So let's make our minimum here equals to, let's do 13.5. See if that works. Okay, so that should work. Okay, so this then enables us to look at our data and try and determine whether or not our data points are actually, whether this process is in control. And just looking at this, I see two data points, one data point above, one data point below the upper and lower control limits. And this tells me that there's a problem that we're having here. Okay, and the problem is that we're not able to control the process. There's something that's going on within the last two time periods here that needs to be checked. Okay, why did we have 14.2 here? Why did we have actually the 3 points actually? So we have 14.8, 14.2, and a 17.3 that are out of control, that are outside of the bounds of our SPC chart right here. So that's something that I would want to check and try and determine what led to those 3 points being out of control. Okay, so that's how you would go about creating an X bar chart in Excel. It's pretty basic. The thing to remember is that you need to know your mean, then you need to calculate your mean of means, and after you've calculated that, you need to ask yourself, what's the Z value that you want to incorporate your data? How large are your samples? And then finally, what's the standard deviation of the sample means? Okay. All right, so let's move on to creating a different type of chart. And that is creating an SPC chart when our standard deviation for the sample of the population is unknown. Okay, so in this first example here, we assume that we had a population standard deviation of 1. Sometimes that's not always the case, and it would be hard to justify that 1 if you don't have historical data. So for example, if we're just starting off a new process where we don't have data which you can rely upon to try and come up with that population standard deviation, then we use a slightly different approach. And that approach involves, again, using the mean of means, which is our X double bar. But now we incorporate something else. We incorporate something called the mean factor, which we get from a table. You never have to calculate this. Okay, and that mean factor just tells you how much emphasis you're going to place on that sample size. Okay, and so a very tiny sample size is usually not recommended. A slightly larger sample size is more useful to us, and that's something that this A2 enables us to capture. The second thing that we're going to incorporate here is our R bar, and R bar is basically just our range. Okay, our range of data of the different data points that we have. So let's try and use the same sample that we had here and calculate our range. Okay, so the first step, again, instead of calculating our mean of means here, now I want to calculate our range. And so I'm going to go ahead here, and for the first sample, which is 1, I'll use a range formula. Now let's do equals max of this minus the min. I used to think I have a range formula, but I guess I don't have it. But that'll give me a range of values that are present in the table. Okay. So basically, what this tells me is that if I took the largest value in sample 1 and subtracted the smallest value from that, I would get 1. Okay. And if I looked in the table here, the largest value is 16.9, and our smallest value, let's see, is that our largest value? I believe it is. Okay, so I get a 1 here, and the reason why that this rounds off certain numbers, so say a 15.8 here, that may not be exactly, and that's also 16.8. Okay, so it makes sense. All right, so this here provides our range. Okay, and that range, these values for the range, the dispersion that we have in our data is what we're going to use over here. Okay, so if you go back to your PowerPoint, if you want to reference your PowerPoint here, your PowerPoint slides, let me see where that, yeah, this is slide number 24 in mine. Yours might be slightly different because I took out certain slides that I didn't need for this presentation. But if you go to this PowerPoint slide here, this will enable you to, if you can't remember exactly what each letter stood for, it gives you all the definitions for what R is, okay? Now, with that information that we have, in this case here, let's go back here, I can get our average for the range. So let's get, it's like our R bar. So this would be called average of what we have here, which is 0.9. And now I can use that information and plug it in here and come up with a number for our upper and the lower control limits. Okay, so let's do the same process. We already have our X double bar as 16. Our A is given here. The thing that we need to know here is what was our sample size, and our sample size was 9. Okay, so given a sample size of 9, our A2 becomes 0.337. Okay, so this would equal 16 plus 0.337 multiplied by R bar, which is 0.9. Okay. Times 0.9. Okay. And this stays the same for the upper control limit. Now let's calculate our lower control limit here, which again would be 16 minus your A2, which is 0.337, multiplied by your R bar, which is 0.9. And that again gives us our range of data for the mean, which is our X double bar, our UCL, and our lower control limit. And with this information, again, we can go ahead and plot, insert with recommended charts, and I'll get this chart here. And again, that doesn't look too easy to see whether it's in control or not, although I can automatically see points outside of the range. So let's format the axis, and again, put our lower bound something slightly higher, say 0. So I'm going to do a 15. No, that's too high. Let's put a 13. let's put this as 15.5. Okay. And with that, now when I look at this, let me put a different tab here. Move chart, new sheet. Okay. So with this now, I look and I see the range of the dispersion for each sample as also not being in control. And you notice that this looks pretty similar to what we had in the X-bar chart. But this tells us a whole bunch of other information. It tells us what samples actually have data that's really dispersed, okay? And so we see that our last two samples here had the largest values and the smallest values was pretty significantly dispersed, okay? Leading to a situation where we have quite a dispersion in our data, and that tells us, combined with the X-bar chart, that something happened within the last, the taking of the last three samples, okay? And so we'd want to use that information and try and control and figure out exactly where did we go wrong with the process. Okay, is there something that can be, is it an assignable cause? Is it that somebody fell asleep while working or something like that? But with that information, now you can go ahead and figure out exactly what went wrong, okay? All right. So the very, yeah, so let's